Continuing with Section 6, Part 1. Here's a description on how to find z-scores from a known area, or probability. First, we draw a picture, and second, we can either use the table and use the area to find the corresponding z-score, or we can use the calculator and the inverse norm function. Below is the notation for critical values, which denotes a z-score with a tail area of alpha. Doing some examples. Example A, we are looking for the z-score with a tail area of 0.05. Let's draw a diagram of what that represents. .05 tail area to the right means that there is 95% area to the left. So we can find the corresponding z-score using the table now by looking for the area of 0.95. Highlighting the two closest areas to 0.95. Which aligns with 1.645. Next example, we want the z-score corresponding to the tail area of 0.02. Which means the area to the left of that z-score is 0.98. So we look for area on the table that has 0.98 area to find the corresponding z-score. Highlighting the area closest to 0.98 on the table, we see that it corresponds to the z-score 2.05. Here, we want a negative z-score with tail area of 0.10. Since the tail area is to the left of the z-score, we can use the table directly to find the z-score. Highlighting the area of 0.10, we can see the z-score corresponding to it. We get that negative 1.28 as the z-score associated with the left tail area of 0.10. Example D, we want the z-score associated to right tail area of 0.025. which means that the area to the left of the z-score is 0.975. Looking at the table, we find that the corresponding z-score with 0.975 area to the left is 1.96. Now let's do it the better way with our calculator. So hit second vars, then scroll down to inv versus norm. Then enter the area to the left of the z-score you want and hit enter. And voila, we get our z-score of 1.645. And we repeat the process for the rest of the examples. Another example. Again, we revisit the degrees Celsius example where mean is 0 and standard deviation of 1. We want to find the first percentile. This is the temperature reading separating the bottom 1% from the top 99%. So let's rewrite this in our critical value notation. And let's draw a diagram of what this looks like. So on our table or calculator, we find the corresponding z-score, which is also the first percentile. That goes with tail area of 0.10. Looking on the table, we get the z-score of negative 2.33, which is also the first percentile. Let's verify this real quick on the calculator. For part B of the example, we want to separate the 0.5% readings that are too low and the 0.5% readings that are too high. So let's draw a diagram of what this looks like. So let's use our handy dandy calculator to figure out these scores. Note that since this is a symmetric graph, the z-scores are going to be opposites of each other. If we have a normal distribution and convert the data values to z-scores, we can use the information for the standard normal distribution. Below are the steps to convert from non-standard normal distribution. Now we do an example. For part A, we want the probability that the selected adult has IQ greater than 131.5. We need to change 131.5 into standard normal, so convert it to a z-score. So let's draw a diagram real quick. Also, let's write in probability notation. Converting the data to a z-score of 2.10, now we can rewrite the probability as p of z greater than 2.10. Also, here's a diagram of the corresponding standard normal. Now we use our calculator to evaluate, hitting second, then vars, and moving to PRB and scrolling down to normal CDF. And our left z-score is 2.10, and our right z-score we choose to be 10. And we get our desired result of 0.0179. Example B, we want probability that a randomly selected adult will be between an IQ of 110 and 120. Writing in probability notation, and then we change each of the data values into z-scores so we can use the standard normal distribution. We get corresponding z-scores of 0.67 and 1.33. Rewriting the probability in standard normal form, and then we just need to enter this in our calculator. And we end up with a probability of 0.1597. Next example. Here we have a mean number of hours on the computer is 3.1 hours per day with a standard deviation of 0.5 hours. We want the probability that a randomly selected worker spends less than 3.5 hours on the computer. Just to clarify, X is the number of hours a worker spends on the computer. Now let's convert 3.5 to a z-score so we can use the standard normal distribution. We get the z-score of 0.80, and now we can use the standard normal distribution. Using the calculator, hitting second vars and scroll PRB and normal CDF. And we get a probability of 0.7881. If we want to find values from known areas, we follow the procedure described here. We can use some algebra to show that this formula for a z-score to get the formula for finding actual values from known areas. And here we have it. So now we can find actual data values when we know an area under the curve. An example. Here we want to know the cutoff separating the lightest 2% from the other. Labeling information and drawing a diagram. We want the critical value of 0.02 tail area to the left. So we use the inverse norm function on the calculator. Using the formula to get the exact value that separates the lightest 2% of babies from the rest. we get that 2,405.25 grams is the data value that separates the lightest 2% of babies from the rest. Another example. This example, we want to find the upper and lower readings that would qualify people to participate in the study. Drawing a diagram, we see what this looks like. We can see we want the z-scores associated with left and right tail area of 0.20. We label them as x1 and x2. Again, using our calculator to find the z-score. So our corresponding z-scores are plus or minus 0.84. Now we just need to use our formula for finding the data value given an area. So we get the lower reading of x1 being 113.28 systolic blood pressure. And x2, we get the upper reading of 126.72 systolic blood pressure.